Take a look at these 3 rows of biscuits. Which one looks most like a randomly ordered sequence to you? I bet you've chosen the one in the middle. The side rows just seem too regular to occur just by chance. There's a formal test to answer the question whether a sequence of categorical or numerical data is random based on the sequence of the individual labels. It's called the runs test, and in this video I'll explain how it works. Let's start with the meaning of the term run in the context of a data sequence. A run is a succession of identical values or labels which are followed and preceded by different values or labels. And the number of data items it contains is the run length. The runs test only considers binomial data. If you have numerical data, it would be changed into values above or below a mean or median, or a series of increases and decreases to make it suitable for this test. And categorical data with more than 2 categories would be aggregated into 2 categories. For example, in this variable with 4 classes, you could consider the class A versus anything else. As the runs test focuses on the ordering of the data, it's crucial that this ordering is unchanged from the moment the data was collected. The runs test counts simply the number of runs in a given binomial data sequence. And this statistic, in spite of being rather simple, gives a good indication of whether the data is random. Because if very few runs occur, relative to the length of the data series, a time trend or some clustering due to lack of independence is suggested. And if, in contrast, many runs occur, systematic short-period fluctuations seem to be of influence. Let's look at an example of how this would work. The local confectioner is making many nice cakes, but for some reason the most popular one is a fruitcake. This may be the case because it's good value for money, or it's a traditional treat. But perhaps there's some interaction between the customers going on in the shop as well. And then you would see that the sale of this cake would not be random, but rather occur in clusters. Let's check this. We take a sample of the sales during a single morning. And our null hypothesis for this test is that the successive sales are not influencing each other. They are independent. Equivalently, you could say that the sequence is random. It turns out that 17 cakes were sold this morning, of which these 9 were fruitcakes. So we have 8 other types of cake that were sold. And if we count the number of runs, we get to a value of 6. Now, how can we decide whether the number of runs is a value so extreme that we would reject the null hypothesis? For small samples, which is roughly when either of the 2 group sizes m or n are smaller than 10, there are tabulated values to find a p-value or rejection region for a given number of runs. But for larger sample sizes, the number of runs approaches a normal distribution. In our example, the sample size of both groups is smaller than 10, and therefore we should use a table here. Let's have a look at such a table. As you see, the table specifies the critical values of the number of runs for each combination of group sizes m and n. The values in the cells are critical levels for the 0.95 confidence interval. So if you find a number of runs that's equal to or lower than the smaller value, or equal to or higher than the larger value in a cell, you would reject the null hypothesis at a significance level of 0.05. In our case, we had groups of sizes 8 and 9 respectively, and we counted 6 runs. As this cell shows, it falls within the confidence range. So the null hypothesis of randomness is not rejected. There is no evidence that sales of fruitcakes occur in clusters or are somehow varying systematically. To finalize, I will also show what to do when you have larger samples. In that case, you can estimate the sampling distribution of the number of runs by normal distribution. Its mean is given by this equation, and its standard deviation by this equation. M and N refer to the sizes of the two groups in the data, and capital N refers to the total sample size, the sum of M and N. Once you have estimated the mean and standard deviation in this way, you can use the z-test to evaluate whether the number of runs is extremely high or low compared to what you expect for your data set under the null hypothesis. Let me summarize what I explained in this video. Independence of data is an important assumption for many statistical tests. But it is an assumption that can also be tested, for example with a runs test. A run is a succession of identical symbols which are followed and preceded by different symbols. The runs test uses binomial data. It counts the number of runs in the data and compares this to the expected number of runs under the null hypothesis of a random sequence. Numerical data can be turned into binomial data by considering the sign of the difference between the data values and the mean or median, or alternatively the sign of the difference between successive values. For small samples, you use a table to find the p-value for the observed number of runs. But for larger samples, the number of runs follows a normal distribution, with this mean and this standard deviation. The test then proceeds as in a z-test.